All right, here's your answer for number 6 for 2016 exam. Give yourself 9 minutes to work through it, and I'll give you the solutions here. This is a challenging problem. And this particular problem, it asks you to relate equilibrium concentrations. You've already read the problem, so I won't reread it to you, but this is what I would do if I were you. If you read a problem like this and you go, I don't know where to start, but I know I have a K value given, you should be thinking equilibrium expression. And you should be able to write that equilibrium expression for the chemical reaction. So I've got that written right here. Hopefully you can get to this. This is a great place to start and start evaluating what's happening in the question. For part A, it says considering the value of K. What does that mean? Considering the value of K. Well, let's consider that value right now. What does this really large value mean? This means it's very, very product favored. Determine the concentration of BA-EDTA in the 100 milliliters of solution and justify your answer. So this is what that means when you consider that. I'll show you the quick way and I'll show you kind of the long way for this. But the fast way is to say it's so product favored that pretty much everything on the left-hand side here is going to turn into the products, everything that we can. So one of these is going to run out. It's a limiting reactants problem because you're given two amounts. You're given 50 milliliters of one reactant with its concentration, 50 milliliters of another reactant with its concentration. So the question is, which one of these runs out first? Well, 50 milliliters times 0.3 gives me more moles of EDTA than 50 milliliters times 0.2. So the barium nitrate is our limiting reactant, and the barium nitrate is a 1-to-1 ratio for barium nitrate for the amount of product that I get produced. And so one of these produces one of these, and that's what I care about, is this product. So all I need to know is what is the concentration of barium ions in the initial solution, because all of it's going to react and turn into my product. Well, your initial concentration is going to be your 50 milliliters times 0.2, that's your moles, divided by 100 milliliters. And another way to think about that is if you double the volume of a solution, so I'll write this out, your barium ion concentration, this is how I would solve it. That'd be your number of moles that you start with, 50 milliliters, times this would be millimoles, 0.20 molar, divided by our 100 milliliters. Well, 50 over 100 is 1/2. And if you double the volume, you cut your concentration by 1/2. So we have 0.01 molar barium ions, and because it's so product favored, and it's a 1-to-1 ratio, we're going to produce the exact same amount of our BA-EDTA. So that's your answer for number 1. This is what it would look like for an explanation. The K value is really large, it goes to completion. Concentration gets cut in half when it's mixed because we double our volume, and therefore the equilibrium concentration must be the same as our initial barium ion concentration. You get 1 point for saying it's the same and 1 point for justifying that. I want to show you another method here because you might solve a problem like this. And if I didn't know where to start, this might be the trail that I go down. I write my equilibrium constant expression, and then I'm thinking, okay, I can write an ice box for this. I'll scoot this over. And I need to know my initial change equilibrium. And the thing that I care about is this value right here, the equilibrium concentration of my product. Well, I just need to know my initial concentrations. So barium, the ion, starts out at 0.2 molar. But we cut that volume, or we double the volume, so it cuts our concentration in half. So my initial concentration for this would be 0.1 molar. The initial concentration for this, starting with 0.3 molar, becomes 0.15 when we double the volume. We have none of this to start for the chemical reaction. We get not plus X, we get minus X here. We're going to shift towards the product side. So minus X, plus X. And we get X at equilibrium, 0.15 minus X, and 0.1 minus X. And now this looks exactly like many problems we've done before in class. You can set that equal to your K value by plugging it into this expression with your X value, solve for X, and you'll get an answer because that K value is so large. Pretty much, when you round it, it's going to be 0.1 molar here. So you could solve that with this method as well. For part B, you dilute the solution with distilled water to a total volume of 1 liter. They want to know after equilibrium has been reestablished. If you see this, after equilibrium has been reestablished, you should be thinking there must be a stress applied because we were at equilibrium already. And now we're not at equilibrium. So what was my stress? We diluted the solution. That's what my stress was. So I apply the stress to my equilibrium position, and I want to know what happens if I apply that stress to my number of moles of barium in the solution after it reestablishes equilibrium. Well, I want to know, does it shift to the left or to the right, or does it not shift at all if I apply that stress? So let's take a look at that. This is a great way to evaluate any dilution problems. If you dilute something, K used to equal Q. So let's take a look at what happens to my Q value if I dilute it. Well, my initial concentration for this at equilibrium is going to be cut to 1/10. I go from 100 milliliters to 1 liter, and so that's going to give me 1/10 of the concentration, with the same reasoning for why if we go from 50 milliliters to 100, we get 1/2. So I get 1/10 of my concentration of my barium, EDTA, and if I dilute it to 1 liter, I also get 1/10 of my concentration of barium ion, and I get 1/10 of my original concentration of my EDTA. So what does this do to my Q value? Well, if we evaluate this ratio here, this 1/10 will cancel with this 1/10. And then I'm left with my K. It's this concentration, my original concentration. So this over this times this is my K value. But I have an extra 1/10 in the bottom. If you divide by 1/10, that's the same as multiplying by 10. Divide by 1/10 is the same as multiplying by the reciprocal, which would be 10. So this is 10 times the concentration of barium EDTA over barium times EDTA. Well, that's just my K value. So this is Q becomes 10 times my K value if I dilute it to 1 liter volume. So what does that look like on a number line? It's a great way to remember what direction it shifts. Put K on there. Q became 10 times my K value. So Q is way over here. We have to shift to the left to reestablish equilibrium if we dilute it. So if I shift to the left, that's going to be shifted in this direction. I'm going to produce more barium ions than I would have originally had in my non-diluted solution. And that would be your justification and your answer. So you should say, we're going to have more. It increases. There's two justifications here. The second one is the one that we just did. You dilute it, you solve for your Q value, Q is bigger than K, it'll shift to the left to reestablish equilibrium. Or you could just say this, the number of moles of barium increases because the percent dissociation increases as solution is diluted. What is this justification? Why is it so short, and how can it be used? Well, if you remember when we first did acids, weak acid dissociation equations, we looked at a weak acid dissociating to produce H plus and A minus, and we considered how do we get the greatest percent ionization. And we solved ice boxes to prove this, but if you increase the amount of H2O, it increases the odds of that HA molecule ionizing. And so a more dilute solution, which has more H2O available, is going to have more H plus and A minus ions produced as a percentage of my original acid. So percent ionization increases when you get more dilute. Well, the same thing applies for this reaction, only we're starting with our compound that's stuck together on the product side. But if I get more dilute, it's also going to shift to produce more ions in this direction, and we'll get greater ionization. And so you could use that for justification as well. The average points for this problem out of 4 were really low. It's one of the lowest ones I've seen is at 0.45. So not very many students knew how to answer that question. And it makes sense. That's a very involved question. But I hope that helps you for an approach for an equilibrium problem. If you don't know where to start and you see a K value, at least if you have time, at least you could start by writing this and trying to figure out if you can do an ice box. But I would, if I was reading this problem and it was on the AP test this year and I didn't know where to start right away, I would skip it and come back to it if you have time, because this test is written long. You might not ever come back to it. And if you don't come back to it, that's probably okay, because if you can't figure out how to answer it and no one else can, then the average is going to be pretty low, and you would want to spend your time on problems that you know you can get points on. So I hope that helps. I'll do one more for the office hour this week for question number 7 on that document. You could scroll down to that question and start working on it now.